So we are ready for Chapter 6, because we're only doing the two sections from Chapter 5. Does anybody have any questions? Does anybody have any questions over the Chapter 5 stuff? Section 5.1 was discrete probability distributions in general, and then Section 5.2 was the binomial distribution, which is a special discrete probability distribution. No questions on that? Okay. Everybody knows what function they're using in their calculator? Either binom CDF or binom PDF. And remember the slides that I showed. I added a slide at the end, and I showed you this at the end of class last time. Remember this one? Right? So this is posted out there on D2L for you to get at. So you can download this. Go to this slide, which is the very last one in the presentation, and then what should you do with it? Put it on your cheat sheet. Right? Put this on your cheat sheet. You don't have to put in all those words, but put this line, put this line, put this line, and you should be okay. Right? When's your next test?
2 weeks from now.
2 weeks from today. That's coming right up. Right? So 2 weeks from today, on I think that's October the 16th. Day before your birthday? But today's the day after my birthday. You guys, I didn't even get any emails from you guys. I'm careful not to announce that thing beforehand. I always wait. No, I didn't bring treats. Okay, so today we are going to start Chapter 6. And Chapter 6 begins with the normal distribution. And I don't like that this book jumps right to normal distribution without really introducing the whole concept of continuous probability distributions and how they differ from discrete ones. So I'm going to do that first, and we're going to be using your calculator to do it. I added a bunch of slides to their slides on this. I'm not going to show all the slides, but just to keep things honest. A continuous random variable differs from discrete, and you already know this, in that you have an infinite number of possible values. Right? So there's no gaps between numbers. So decimal places are possible. And at least theoretically, we could measure to however many decimal places we wanted, we could get an infinite number of possible values for a continuous variable, like height. If I measure your height, right, I could have an infinite number of possible values even between 5 foot tall and 6 foot tall, because any number of decimal places are possible. Okay? So the distribution of a continuous random variable is called a continuous probability distribution. And the values from a continuous distribution are measured, probabilities are measured on intervals. Okay? So here's why. Let's introduce a very simple probability distribution called a continuous uniform distribution. All right, so uniform. We've had that word before when we talked about distributions. What does it mean? What was a uniform distribution?
Bell-shaped.
Not bell-shaped. Flat. Right? It was horizontal all the way across. So every value is equally likely. Well, you have one of these built into your calculator. This very one, this is called a uniform 0-1. So random number generators that return a random number between 0 and 1 is called a continuous 0-1, or I'm sorry, uniform 0-1 random variable. Its probability density or probability distribution function would look like this. Now remember, we were doing binomial distribution, we did some others, and we drew pictures of the distribution. When they're discrete, they look like bar graphs. When they're continuous, think about bar graph for like pulse or height or something, but you take smaller and smaller and smaller intervals, pretty soon you get a smooth curve instead of a bar graph. So a continuous distribution has a smooth curve. Now this one is uniform 0, 1, so A would be a 0 and B would be a 1. Right? So it's horizontal across there, indicating that all values are equally likely. Right? Now, I'm going to shut this off for a second. I want you to get your calculators out. And in your calculator, you have this function built in. So, did everybody bring their calculator today? Nobody without? Awesome. Claire. Test that back. You don't have one? You're just SOL. I mean, out of luck. So you'll have to just watch on his. Okay? So, push the math button, then go over to PRB. Guess what PRB stands for?
Probability.
Probability. The very top thing that you'll see there is 1:rand. That's short for random number, right? Press enter, and you get the word rand on your screen, so press enter again. And you should get a random number between 0 and 1. Right? What did you get? What did you get?
0.6614.
Okay, 0.6614. What did you get?
0.9436.
0.9436.
That was really close to mine.
How many people got 0.9436 something, something, something? I wish they could see this. 3/4 of the class have their hands raised. Why is that? Why do you all get the same number if it's a random number between? Well, because there's no such thing as a true random number generator on a computer. The only true random number generator would be like a bin of balls, and you rotate it around and out pops ping pong balls or something, right? So calculators is called a pseudo-random, and it comes from the factory preset with a certain random number seed, and none of you have used your function before, so you're all sitting at the first number in the sequence. Right? So you all match. Press enter one time. Now what'd you get?
0.4986.
Oh, you're the one that was different though. What'd you get?
0.9083.
0.9083. Everybody get the same number? Press one more time, you'll match again. Now, so what we got to do is we got to get you all out of sync. Right? Because all calculators will have that same sequence of numbers, but you just have to get out of sequence with each other. So just close your eyes and wail on the enter button a whole bunch of times and don't count how many. And then stop.
It's okay.
Because I hit cool.
So you're up.
Yeah, I'm already.
Okay? Now, push clear. Press enter one more time. And you should all be out of sync. What'd you get this time?
0.0078.
0.0078. Anybody else get that number? You're lying.
I swear.
Okay, do it one more. Hit one more. See if you stay, because if you're still in sync, then you hit exactly the same number of times.
So hit it one more time.
You. What'd you get?
0.9351.
Okay, so you hit yours a whole bunch more times. Okay.
Now he may be
I hit mine 3 times more than that.
Okay, it's not that big a deal. Right? So what you get is a number, and if you look at it, I've already counted it, but if you count, it's giving you 10 decimal places. Right? So any number between 0 and 1 is equally likely. It's uniform. So what is the probability that x is equal to 0.3, let's say?
It only gives you 9 numbers.
Is it 9?
Some of them go out some good time. That's all I'm breaking.
Okay, yours is broken. No, I'm just kidding. It doesn't matter. It's close enough. So most of them we get 10 decimal places, right? So what's the probability of getting 0.3?
Just 0.3.
What?
Just 0.3.
Yeah, just 0.3, not 0.3 something, 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 something. 0.3000000, or just 0.3 with nothing.
One out of
Did you have an answer?
1 out of
Yeah.
1/10 rad.
How many numbers are possible if we go to 10 decimal places?
So
10 to the 10th power, right? Because you got 10 blanks, could be filled with 10 digits. 10 to the 10th power is 10 billion.
1.3.
So this probability would be 1 in 10 billion. Did anybody get 0.3? Press enter again. Did you get it?
No, I just know.
I got 428.
Keep pressing enter till you get 0.3. Oh, and by the way, if you get 0.3, I'll give you $1 million. Not 0.3 something, something, something.
0.30.
0.30 with nothing but zeros after it.
Give me a minute.
Oh, shoot, she said.
how long do we have?
You just
Right.
typed it in.
We change the programming on this.
Yeah, if you can hack into the computer and change it, right? So why am I safe saying I give you $1 million?
Because you have 1 in a billion chances.
Because there's a 1 in 10 billion chance that you can get that number. What was the probability you win the Powerball lottery?
About that.
No, much better than that.
That's weird.
1 in 146 million.
Sometimes it gives
And you saw how unlikely that was. 10 billion is a huge number compared to 146 million. How many 146 millions fit into 10 billion? A lot, right? So it ain't going to happen. So the point is, for a continuous distribution, the probability of getting exactly equal to any specific number is 0. Right? It's 0. So think about the distribution of height, a continuous random variable. What's the probability that you measure somebody and they are 6 feet tall, which is 72 inches? What's the probability that you could randomly select an individual from the population and they are 72 inches tall?
Highly unlikely.
And by that I mean exactly 72 to an infinite number of decimal places. 0 chance. It cannot happen. So that's an oddity of continuous distributions, is that every single value has 0 probability associated with it. Yet, if I ask you this, what's the probability you got between 0.25 and 0.5? What's that probability? Well, the probability of an interval we can figure out. So when you have a continuous distribution, you can talk about probabilities of intervals, but not probabilities of single numbers. Hit enter one more time, and raise your hand if you get a number between 0.25 and 0.5. Raise your hand. Raise them high. Only 2 people? Oh, 3? Are the rest of you cheating? What'd you get? 0.94? Okay. So 3 people out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Right? So 3 people out of 22. What's 3 out of 22? Besides being too small?
0.136.
0.136, so about 13% of you. What's this probability? Well, remember the graph that I showed that had a horizontal line between 0 and 1? It turns out that the area the probability for intervals is just the area under the curve within that interval. So 0.25 is right there, 0.5 is right there. What's that area? 25% of the total area. It's 25% of the possible values. Right? Now, how tall is this graph? It's kind of a trick question because I haven't told you, but you should be able to figure it out. What'd you say?
1.
1. How'd you know? That's right.
Because you can't go above 1 in order to be a population.
Oh, no, that's not the reason.
It's not the reason.
I could draw a normal shaped curve that goes way up here to 20 or something, right? Probability can't be over 1, but the height of the curve can be.
Because n is 1.
What's the total probability The total amount of probability. 1. In other words, if I say hit enter one more time and I ask, how many people got a number between 0 and 1? You would all raise your hand. 100% of you would raise your hand. Right? There's a 100% chance you're between 0 and 1. So the whole area, the whole curve has to have an area of 1. And since its width is 1, its height must be 1. Right? So then the area of the shaded region is 1 unit tall, 0.25 units wide, or 0.25. So the area under a continuous probability distribution curve is just the probability of being in that region. So let's look at, remember our data that we collected, and we had women's heights. We had a mean of about 64. And I'm treating it as if that's the population mean. And we had a standard deviation. Do I remember what the standard deviation was? It was about 3, right? Then what did that distribution look like? What was the shape of it? It was bell-shaped and symmetric, right? So if I draw a bell-shaped and symmetric curve and center it at the mean, which is 64, and then go plus and minus 1 standard deviation, how far out does that take me on my picture?
Halfway down the hill.
Halfway down the hill. Very good. So halfway down the hill at what's called the inflection point would be 3 units above 64. 3 from the standard deviation. So 3 units above 64 would be 67. And 3 units below 64 would be halfway down the hill going the other way, or 61. Right? This particular distribution that is symmetric and bell-shaped is known as a normal distribution. I've already given you that term at some point during the semester. It's also sometimes referred to as a Gaussian distribution, named after the guy that invented it. I don't know if that's the right word, but I don't know if you discover a function or what. He came up with it, right? But he did discover that, hey, this curve with this particular mathematical equation seems to fit an awful lot of distributions, right? So it's called Gaussian after Frederick Gauss, or more often called the normal distribution, right? Now, what would the distribution for male heights look like? It was also bell-shaped and symmetric, so we'll say it was normal,
Be shifted to the,
but it was shifted. Do you remember how much?
It was around 6.
Yeah, about
5.
6 inches taller, maybe 6 or 7 inches taller. I think it went from 67 to 71, so that'd be 7 inches taller, right? So there are an infinite number of normal distributions. A normal distribution is completely determined by its mean and its standard deviation, right? You tell me where to center the thing, you tell me how wide to make it, and I can draw you a bell-shaped symmetric curve that has what total area under it? What's the total area under this curve? 1. Very good. Just like this. Any probability distribution, you've got a total of 100% or 1 probability to distribute. So the area under a continuous distribution is the probability, so the total area has to be 1. Total area under equals 1. Okay? Now, what's the probability that a randomly selected woman is between 64 and 67 inches tall? 68%. How'd you get that? The empirical rule. Very good. So that's about 0.68, right? What's the probability that a randomly selected woman is between 60 and 66 inches tall? Smarty. The answer here is, I don't know. You haven't taught us how to do that yet. I can do it if they're nice integer multiples of the standard deviation, but otherwise I need another way to do it. That's what we're going to do now. Right? So to do that, I'm going to introduce you to the standard normal distribution, and we'll talk about that. We'll work some problems from it, but I want to say the book emphasizes the standard normal distribution way more than I will. Okay? And the reason is because, like I said, there's an infinite number of normal distributions. But one of the ways to compute probabilities is to look at the normal tables in the back of the book. Right? Normal tables. You look up probabilities. Well, you can't put an infinite number of normal distributions in the back of the book. So you convert everything to a standard normal distribution. So the standard normal distribution has the same bell-shaped symmetric curve, but it's centered at 0 and has a standard deviation of 1. Okay? Now, here's where it comes from. Let's come back over here, and I've got, I want to know the probability of being between 60 and 66 inches tall. Well, how many standard deviations below the mean is a 60-inch tall woman? How many standard deviations? 1 point something, yeah. What do you compute to know that? What is it that we've learned in the past that gives us number of standard deviations? Z-score, very good. So Z-score is x minus the mean divided by the standard deviation. Remember this? So what's the Z-score for 60? Well, you take 60 minus 64 divided by 3, right? 64 is the mean, 3 is the standard deviation. That's negative 4 over 3, which is negative 1.33 repeated. Okay? Now, on my graph here, if this is 61 and this is 64, then there's 3 units in there, so I need to go 1 unit back this way to find where 60 is. So there's 60. Right? And then same thing, 66 is 1 unit back left of 67, so that'd be about right there. Now I want this region. I'm going to shade the region that I want the probability for. Okay? Give me a ballpark estimate of that shaded area.
Close to 68.
Good. Close to 68. Now, think about it, and you can probably go one little bit better and say, is it going to be a little above 68 or a little below 68?
Below.
Look what I subtracted off. I didn't mean to shade all the way over there. Look what I subtracted off from 68, and look what I added back on. So this one's a little taller. So I'm going to be a little less than 68. So I've got a ballpark idea in my head that, oh, it ought to be 0.6 something, but a little less than 0.68. Right? Now, why do we go to this trouble to draw pictures and get a ballpark estimate? So that when you do it on your calculator, you get a wrong answer, you can look at it and go, ooh, that doesn't make any sense. And you can go back and find your mistake. Right? So go to that effort. Find a ballpark estimate. Okay? Well, let's keep going here now. 66. What's the z-score for that? You do it and tell me what the answer is. Okay, I heard somebody say 2/3. 66 minus 64 is 2 over 3 is 2/3, so 0.66 repeated. So this probability is exactly equal to the probability of a z-score being between negative 1.33 and 0.66 repeated. Right? Those probabilities are going to be the same. That's the beauty of this standard normal distribution. You can convert to z-scores, get exactly the same probability you're looking for, but based off of a distribution that is in the back of some book or whatever. Right? But like I said, I'm not going to emphasize this one so much because we have all the infinite normal distributions built into our calculator. We don't have to convert things to z-scores first. But your homework, you have to. Because that's all the section 6.1 and 6.2 homework, they all convert to z-score first and then they compute it. Right? So we're going to work with the standard normal distribution just to get the feel for estimating probabilities on a normal curve. And then in section 6.3, we'll actually learn how to compute ones for distributions that aren't standard normal, like this one. Okay? So, here's how it works. Let's find the probability between negative 1.33 repeating for a z-score and 0.66 repeating. First thing, what's your first step? Draw the picture. What's your second step? Label the standard deviation lines. Third step, mark the interval that you want the probability of. So where is negative 1.33? Well, if this is 1 unit, that would be a 2. And 1.33 would be 1/3 of the way, so about right there. Now where's 0.666? 2/3 of the way from 0 to 1. So that's about there. Now shade that region. Now notice this region is exactly the same as this region. Right? So the book will take you through the steps now to look up the numbers in the back of the book in the normal table, do a bunch of addition and subtraction and come up with the probability, and that's fine. I've stripped all that stuff out of the PowerPoint presentations that I'll post for you because I'm going to let you forget about that. So when you go into the Hawks learning system and you go through the Learn module, they're going to go through all that stuff with the normal table. You can just ignore all that, fast forward through it, go right to where they start working on the calculator. Okay? So here's how you do it on your calculator. This probability is equal to normal CDF. So where do I find normal CDF? Well, it sounds kind of like the binom CDF, so it is in the same place. Where do you find it? Second function. Then the vars button, which has DISTR written above it. And then go down to normal CDF. Right, now while we're there, let's pause for a second. If you look at it, it says, when you go into DISTR, you see the top one says normal PDF. The next one says normal CDF. And the one below that says inverse norm. INV norm. Right? So top three are all normal distributions. The PDF, when we did binomial distribution, the PDF was the probability of being exactly equal to something. But this is a continuous distribution. What's the probability of being exactly equal to something in a continuous distribution? 0. So we don't need PDF ever. So delete it from your calculator. Go ahead, do it. Okay, you can't. But if I could, I would delete it from your calculator, because on a test, somebody will use the normal PDF when they're supposed to be using the normal CDF, and they'll get the answer wrong. But that's part of why I want you to get a ballpark estimate of the answer, so that when you do the wrong thing, you look at your answer and go, well, wow, that's not what I was expecting, and you'll catch your mistake. Okay? So, normal CDF. We've got two types of calculators, old style, new style. The old style, when you hit enter, it puts this on the screen with an open parenthesis and a blinking cursor, and it's just waiting on you to fill it out. The new style tells you what it's expecting, right? So somebody have a new style, it'll say below it, what does it say?
Lower, upper,
Lower, upper,
mean,
mean,
sig-
standard deviation, which is a sigma, you're right. Okay? So that's what you're going to enter. There's 4 things that you enter. The first one is lower, second one is upper, and then mean and standard deviation. What the heck does lower and upper mean?
your bound.
The bounds of the interval you want the probability for. So this is the lower bound, this is the upper bound. I stood in one place too long and the lights went out. Right, so lower bound is negative 1.33, and enter about 4 threes. That should be good enough. And then 0.66, and it would round to 6667. Now, what's the mean and standard deviation for standard normal? 0 and 1. So you can enter 0 and 1, or as the book tells us, if you just close the parenthesis here and hit enter, it'll work. As long as you want 0, 1, because that's the default. But that's a bad habit to get into, because eventually I'll make you do ones over here, and you'll just hit enter, and it'll use 0, 1 when it should be using 64 and 3. Right? So if you just go ahead and type them in, 0, 1, you'll get in the habit of always entering those values. All right, so then do that, and tell me what you got as an answer. 0.6566 63. 0.6563 rounding to 4 decimal places. Everybody get that? All right, she did not get that. What is your name? Maddie, that's right. Help her. Did you get that number? Oh, you didn't get it either. Help her. And then she'll help her. Right? Okay, so we got that. So the interpretation of this is that about 65% of women should be between 60 inches tall and 66 inches tall. Right? All right, let's do another one. I guess I'll do it here. I want you to do this one. Probability that Z is less than or equal to negative 1.4. Z is less than negative 1.4. What's the first step? Draw the picture. See, you already were pushing buttons. I can see it. Draw the picture. Label where 1.4, you can recycle your picture, but label where negative 1.4 is, and then shade the region that they ask you for the probability. That will help you figure out what's my lower, what's my upper. So draw the picture. This is standard normal, so it's 0, 1. So 1.4 is about right there, and I want that region. Okay? Now this one's kind of tricky. What's my lower?
0.
No, because 0 is right there in the middle.
Negative.
Negative infinity. Oh yeah, I'll just got to enter negative infinity. Well, negative infinity is a whole bunch of 9s. So enter negative 9, 9, 9, and keep going until infinity. I hope you have the rest of your life. But guess what? You don't have to go all the way to infinity. You just got to get a really big number, right? And remember, the empirical rule tells us that by the time we get to 3 standard deviations or 4 standard deviations, there's hardly anything left. So if I go to 99 standard deviations, that ought to be plenty. So negative 99 is enough for standard normal. But what the book tells us to enter, and this is a good habit, enter negative 1 and then EE 99. And the EE is scientific notation. So the EE is above the comma button. Everybody find the comma button? So you push second function comma. So negative 1, second function, comma, 99.
Do we do it once? When you do it once, it just comes up E.
Well, you have to then enter your upper bound.
Does it, when you hit second E, it just...
Oh yeah, there's only one E showing on the screen, but it has an E. I never figured out why it did that. Which is why I kind of bail out and I just go negative 9, 9, 9, 9, 9, 9. Just enter a bunch of 9s and you're fine. Okay? So you're going to enter normal CDF, negative 9, 9, 9, 9. The number of 9s that you need if you do it this way depends on the scenario of your problem. If you're doing standard normal, then 2 9s is enough. If I'm doing incomes, and I have some of the incomes are $500 million a year, I need a lot of 9s to get way bigger than that. Right? So use your own judgment. And then negative 1.4 for the upper, and then 0 and 1. And what do you get?
1, 0, 0.
And you know what I forgot to have you do first was get a ballpark estimate of this before you do it. So to get the ballpark estimate, what would the probability be from the dotted line to negative infinity? From the empirical rule? 16%, right? Because remember, in the middle is 68%, leaving 32% that's not in the middle. Half of that 32% would be up here, half would be down here. So I know I'm going to get a number less than 0.16. But at negative 2, I would have 2.5%. So I'm going to be somewhere between 2.5% and 16%. So it looks like it's about halfway in between there. So let's call it, I already know the answer, 8%. So you should get a number around 0.10, 0.05, somewhere in there. So what did you say it is? 0.08? 0808?
Yep. 0749.
0749. Well, it might have to do, what did you enter here for your lower?
The 999.
Are you sure you didn't put a decimal in there? Because if you put a decimal there, that's a common mistake. You put a decimal there, what happens? That's basically negative 1. So you're going negative 1 to negative 1.4. That's this little region right here. You don't want that. Show me yours after class, and we'll figure out what went wrong there. Okay, everybody good on that? Everybody get that number? Okay? Do this one. Probability that Z is greater than 2.8. And I'm going to come around and look at what you do. I want to see all steps. I want to see a picture. I want to see a shaded region. I want to see a ballpark estimate. Then I want to see you go to the calculator. Give me a ballpark estimate. Just guess. And sometimes these ballpark estimates, they don't have to be any more accurate than, ooh, that's going to be really small, or ooh, that's going to be really big, right? What do you think? Look at what you shaded. Um, 1.5%. When you said 1.5, I was having to clarify because the probability can be bigger than 1, but you meant 1.5%, so 0.0. Okay, now I don't like your picture. And this, I was just glanced from a distance, and she did the same thing that half of my last class did and half of you were doing. She wrote her 0, sorry to pick on you, by the way. She wrote her 0, and then she went to the dotted line and put a 2 under it. Why put a 2 under it? Well, because there's a 2 in the problem, right? But what goes under that dotted line? 1. You go out 1 standard deviation, that's a 1. So 2's out here, right? And you have to be careful with these pictures or they don't help you. The idea is to help you catch mistakes, but if you're not careful on how you draw it, your guess is going to be way off. Okay, I don't like your picture real good. It's okay, but let me see this. This is my measuring stick. This is 1 unit.
Right.
So there would be 2 units. You put 2.8 beside it. Right? So there's 2, and there would be 3, so 2.8 is more like way over there, right?
Yeah, yeah.
Oh, that's why you missed the first one, because you said 4.4. I just had 4. Negative 1.4.
okay.
Check your you notice you got a negative value?
I know how to do it.
And probabilities can't be negative. All that means is you reverse. You're 9999. But this is supposed to be 2.8. So you're going to be off a little bit. Okay, that looks really good. I like your picture. Now, where's your ballpark estimate? Okay, good. And then you did it, and you got some. Okay, yeah, very good, very good. See your. Okay, looks good. You said really small. Okay, good. Okay, that's the right answer. Good. And this was your estimate?
That's the bottom one. That was nice.
Okay, what's your answer? With the negative sign?
That's the.
Can probability be negative?
Is it not a negative?
It's not a negative.
Well, then that's right.
Okay, good. Okay, that's a good picture. Only here's your axis. You're shading way down below. You know what I mean? So, okay, that's the right answer. Where's your picture? Good. Where's your ballpark estimate? Okay, good. Okay, most people are getting it with me. They listen to me hit the first people I look at are always, if I'd start on this side of the room, then they'd have been the ones I was making fun of. But you have to get fairly good at this. Halfway down the hill is always 1 standard deviation. It has nothing to do with the interval that you're looking for. This one was 2.8. So draw it first, and then use your fingers as calipers if you need to. Okay, that's 1 unit, so there's another unit, there's another unit, and 2.8 is going to be way out there, right? So there's my shaded region. So ballpark estimate is?
Small.
Really small, right? A really small probability. In fact, if it were 3 out, it would be half of what's left over from 99.7%. Remember the empirical rule, 99.7? So half of 0.3% or half of 0.003, which is 0.0015. But it's going to be a little bigger than that because 2.8 is a little further in. So 0.002. Good ballpark estimate, right? Now, some people we're getting some weird answers. I saw 0.9788 something.
Did they switch around their upper and lower bounds?
Not quite. That's the next common mistake. What did they do?
It was negative infinity.
They went negative infinity up to 2.8 instead of 2.8 up to positive infinity. So they got this region. And how does your ballpark estimate help you catch that mistake? You expect a really small probability and you get a really big probability. Oh, I bet I flipped it around. Now, some of these people got negatives, right? Can probabilities be negative? No. Well, why does the calculator give me a negative number? Shouldn't it be smarter than that? Well, it's not. How do you get a negative? You just reverse your lower and your upper. And it's an integration tool. So do you remember from calculus, those of you that had calculus, if you integrate the opposite direction, it's the opposite, right? You get a negative value. So that's what the calculator is doing. So if you ever get a negative probability using normal CDF, just look and see, well, I must have switched my upper and my lower. So if you go positive infinity to 2.8, you'll get negative 0.0025 or whatever. Okay? Everybody happy? Still got 2 minutes to kill. It's Friday before fall break. Okay, now I want you to remember these 2 minutes because I'm going to take them back every class period from now on. Oh, remember, you guys owe me 2 minutes. All right, have a great fall break. You've got homework tonight over section 5.2, and then this homework will be due next Wednesday. So you have no homework due Monday. We'll see you then. Have a great break.